হ্যালো,
Yes, sir.
চেক করবো?
হ্যাঁ স্যার। Yes, sir. Absolutely fine. স্যার ওয়েবক্যামটা একবার অন করে দিয়ে তাহলে ভিডিওটাও চেক করে নিতে হবে।
হ্যাঁ, ওয়েবক্যাম অন করেছি আমি। আসছে না? দেন একবার লেট মি চেক। এবার এসেছে? আমার এখানে দেখাচ্ছে স্টার্ট করতে হবে, দাদা।
হ্যাঁ, ওই যে স্টার্ট ওয়েবক্যাম শেয়ার। শেয়ার ওয়েবক্যামে স্যার বাটন ক্লিক করতে হবে।
এবার এসেছে?
হ্যাঁ স্যার, অ্যাবসলিউটলি ফাইন। থ্যাংক ইউ স্যার।
দেন এবার আমি একবার এটা চেক করে নিই। সে
হ্যাঁ।
এসেছে এবার?
হ্যাঁ স্যার, এসেছে। ঠিক। ওকে স্যার, থ্যাংক ইউ।
বাট প্যারালালি দুটো দেখা যাচ্ছে না আমার স্ক্রিনে, মানে ওয়েবক্যাম প্লাস সেটা জানি না কেন।
স্ক্রিন শেয়ার করলে স্যার অ্যাকচুয়ালি হওয়ার কথা, মানে শুধু আপনি শেয়ার করলে আপনার শুধু স্লাইডটাই দেখা যাচ্ছে।
হ্যাঁ 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 হ্যাঁ, কিন্তু অডিয়েন্সের কাছে দুটোই দেখা যাচ্ছে।
হ্যাঁ, অডিয়েন্সের কাছে দুটোই দেখা যাবে।
ঠিক আছে, ওই এটা ভিডিও ওয়েব ক্যামটা কিছুক্ষণ পর অফ করে দিতে হবে, কারণ নাহলে আবার নেট ফেটে যদি প্রবলেম হয়।
আচ্ছা, নো প্রবলেম।
হ্যাঁ,
ঠিক আছে।
হয়তো কিছুক্ষণ পর অফ করে দিতে পারি।
হ্যাঁ।
ফারুকদা,
হ্যাঁ বলুন। বলুন।
হ্যাঁ বলি স্যার অলরেডি জয়েন।
হ্যাঁ হ্যাঁ স্যার,
গুড মর্নিং স্যার।
গুড মর্নিং স্যার।
স্যারের সাথে টেস্টিংও করে নিচ্ছি।
ওকে ফাইন।
আলোক স্যার, আমার অডিও আসছে?
হ্যাঁ আসছে, কোনো অসুবিধা নেই, ফাইন।
গুড মর্নিং।
গুড মর্নিং স্যার।
ওকে, গুড মর্নিং।
স্যার আমার ক্যামেরা ঠিক আছে?
হ্যাঁ ফাইন। তনুশ্রী, আমরা তো স্টার্ট করবো কত?
আরেকটু
27।
পরে,
হ্যাঁ হ্যাঁ, another 5 minutes we can start
5
the
মিনিট
session.
পরেই তাহলে স্টার্ট করে দেবো।
হ্যাঁ হ্যাঁ, ওকে ওকে ফাইন।
Dilip sir, we can start now, I think so. So good morning. So we have come to the day 4 session of the online FDP, and today's session will be taken by Professor Shibendu Shekhar Roy. He's from National Institute of Technology, Durgapur, India. He will be talking on the topic materials for additive manufacturing. Dr. Shibendu Shekhar Roy received BE and MTech degree in Mechanical Engineering from NIT Durgapur. He also holds a PhD from IIT Kharagpur, India. He is currently working as a professor at the Department of Mechanical Engineering and Associate Dean, that is Alumni Affairs and Outreach at the National Institute of Technology, Durgapur. Dr. Roy has published more than 68 papers in national and international journals and conference proceedings, as well as 4 book chapters, and has filed a number of patents in the area of product development. His current research interests include modeling and simulation-legged robot, soft robotics, rehabilitation of robotics, additive manufacturing, and 3D printing on micro and macro scales. Now, I will request Sir to please start the session.
Hello.
Yes, sir.
Am I audible and is it visible, the slide?
Yes, sir.
Okay, very good morning to all of you. First of all, I like to thank the organizer of this AUTOL program for giving me an opportunity to share some of my experience in the field of additive manufacturing. Topic of my today's talk is the materials for additive manufacturing. And its outline of my talk, I like to introduce the additive manufacturing or 3D printing, and one of the important additive manufacturing or the metal additive manufacturing I like to introduce. After that, it's followed by, or simultaneously, I like to mention what are the materials used in additive manufacturing and what are the future research direction in this particular area. So as you see, the manufacturing technology or manufacturing processes in the domain of mechanical engineering and domain of metallurgical engineering, it's broadly classified into 4 groups. The first and foremost is the formative processes, which is also known as near net step manufacturing. And depending on the initial state of material, it may be liquid state, the liquid state formative processes. The processes are the castings and the injection molding. So in solid state, its processes are your metal forming. So different kinds of metal forming, like rolling, forging, deep drawing, sheet metal working. So these are the few metal forming process which the process is carried on over the solid state, either hot rolling or hot metal forming, or the cold metal forming. So another class which is one of the promising one is the powder state or the powder metallurgy based manufacturing processes. Now we have to do finishing of the. You have to get the desired shape and size. For that, material removal or subtractive manufacturing process is essential. So second group of manufacturing is the subtractive or the material removal processes, like conventional machining processes or unconventional machining processes. So conventional machining process, it is by turning, milling, drilling. So these are the conventional machining process. The unconventional machining processes are electro discharge machining, electrochemical machining, laser beam machining, ultrasonic machining, and nowadays in modern era, so there is a hybrid machining, the hybridization of the different conventional and unconventional machining processes. So there are many third group is the fabrication process. So there are the different joining processes like the welding, brazing, soldering. So there are the different class of welding processes. So these are the basically used for fabrication work. But nowadays I like to tell you, joining process is also used in the area of additive manufacturing. Here the additive manufacturing is the youngest member in the family of mechanical manufacturing processes. So which previously known as rapid prototyping, but now that's per ASTM its name is additive manufacturing and popularly known as 3D printing. So today's topics is on the additive manufacturing or the 3D printing processes and corresponding material used for this particular process. So we like to introduce for the additive manufacturing process, and this is one of the disruptive manufacturing technology in the modern era. And once upon a time, it was a dream for design or manufacturing technologies to develop such a technology as the potential of directly converting the CAD data into the real object. That means a technology provides the bridge from the product conceptualization to product realization in a reasonably faster manner. Now it is in reality through the additive manufacturing process. So it is a process of joining materials or adding materials to create object from the 3D CAD model. Usually layer upon layer, it is opposite to the subtractive manufacturing methodologies. So additive manufacturing process where the materials are added, joined layer after layer. It is very close to the way our nature is manufacturing many things. If you see the bank of river, you can see years after years, the soil has been deposited and it has been formed such a kind of a landscape or the island kind of landscape. So this is basically one nature developed thing or nature manufactured thing, which is nothing but adding material or adding soil layer after layer. Similarly, in nature, you just see plant, animal, insect, even human being are basically developed by adding material, not by subtracting material. It may not be the layer by layer. It may be the the cell by cell like that way, but it is adding material. So that is why additive manufacturing is very close to the way the nature has been manufactured many things. Now, if you compare with the additive manufacturing with the subtractive manufacturing process, it will be clear that in subtractive manufacturing process, you have to take a bulk material and you have to give desired shape and size of this bulk material by removing the material. And that removal of the material to give the desired shape and size is basically wastage. Most of the time, some portion can be recycled, but you can treat this as the wastage of the material. But in case of additive manufacturing, you just see you will add material wherever is required, depending on the cross-sectional information. Wherever is required, you add material, and that is why here the wastage is less. So this is one of the important benefit of using additive manufacturing. Now, what is the basic principle of additive manufacturing? So it's similar to the way that you see any sculpture, this kind of surface. you can create the sculpture surface like this. You can create by removing the material. You take a bulk of material, rectangular piece, and you remove the material by machining process, or you can by casting process, you develop the mold, and you can do the casting process. But the way, the other way you can also develop like this. You just take each cross section, have a different cross section. You just cut a cardboard, and one after another you can glue it. Like the way it is, one after another you glue it, and each cross section is a different geometry according to the shape of this. So by adding this particular cardboard kind of thing, by gluing this one after another, you can develop this 3D object. So this simple principle is used in additive manufacturing. But how will do that one? So in order to do that one, you have to develop the CAD model, computer design model, in any CAD tools or any CAD software. And then what you have to do, there is a slicing. So any 3D CAD model, you have to slice it. The slicing means horizontally you have to split into the different planes. So the way it has been done. So that means here we are converting the 3D CAD model into number of 2D geometries, 2D cross-sectional geometry stack one after another. And this is basically stored into the CAD database. And according to the each cross-sectional information, material will add over the build platform, one after another, moving from say downward to upward, and you will get the solid object. So this simple principle is used in additive manufacturing process. The same way the nature is also developing, adding material layer after layer from bottom to top. Reverse way also you can do nowadays, but in generally it is the bottom to top. Now, what are the steps involved in additive manufacturing? First, you have to develop the 3D CAD model of an object. Then you have to convert into the neutral file format, .htl format. Then you have to generate the support structure. So some overhang structure, you have to put a support. A support should from the bottom. For example, you see, whenever you like to develop a water tank or any cantilever kind of thing in your civil structure, so you have to give support of the different structural members, support member, like the different type of scaffold using bamboos or using the metallic pipe. So similarly here also, if there is any overhang structure, you have to give the support in CAD model. In CAD model itself, you have to design the support. After designing the support, you have to slice. Slicing means it is the intersection between the solid and the plane. Ultimately, you will get the cross-sectional geometry that will be stored into the CAD database. And that slicing data, suppose a particular object, depending on the height, it may slice, say, 1,000 layers or maybe the 50,000 layers. So depending on how much pre-processing. So slice it, the slice, that means you're converting the solid model or into the number of 2D geometries, and that will store into the CAD database, and that will feed to the machine. And according to the cross-sectional information, the machine will deposit the material over the build platform layer after layer, and it will create the object. Now, how will add the material? So that is the important issue that I like to discuss. What are the material used and how that addition has to be taken place? Once it is developed, your physical model has been developed, then you have to do some post-processing operation like cleaning, post-curing, post-work, finishing it, depending on which particular methodology you like to use. And ultimately, whatever you will get, that is the component for the prototype, or pattern for the complex component, or it may be the functional parts. But one thing you have to remember, as this particular process is still, it's a costly one, and better to use when your geometric complexity is more in a particular component, and when there is not required for the mass production, rather when there is a requirement of mass customization of the complex shaped object. It will be the better for additive manufacturing. But you will get additive manufacturing can develop any geometry, simple, complex, whatever you like. But its benefit will get when your geometry is complex, when your traditional manufacturing processor fails to build that particular component of complex geometry, that time better to use additive manufacturing process. Now, if you compare that 3D printing, additive manufacturing, also known as 3D printing, with the 2D printing process, as you know, that in 2D printing we are using in your office and in your house. So in 2D printer, we develop the digital model, either in Word or PowerPoint or Paint, whatever may be. That will fade to the printer, and in printer you just see, if it is an inkjet printing system, there is a ink head. Head is inside, your head will be there, and head will move in a, say, like this direction, let us say X direction, and your paper will move in a Y direction. Head will move X direction and paper will move Y direction, and one single layer ink will be deposited, and the tiny nozzle is there, array of tiny nozzle is there. Through that, nano droplet of the ink will deposit, and printing will over only one layer. So there is two movement, X and Y. In case of a 3D printing, you just see, you have to develop a 3D CAD model, slice it, feed into the machine, and here you just see there is a build platform here. Over the build platform, according to your cross-sectional information, because you have already split into the number of cross-sections. So according to the cross-sectional information, there is a head, there is a, say, nozzle, there is a head. Through that, material will deposit. So that head will move in XY direction. It will move X direction as well as the Y direction to deposit the material over the bed. It will deposit the material over the bed. Like this way, it will deposit the material. Once one layer deposition is over by XY movement of the print head, then the build platform is lowered down. Build platform is lowered down in a Z direction, equal to the one layer thickness. That means there is 3 movement is required, X, Y, and Z. And that way you can, it will develop a 3D model or 3D prototypes. So that is why it is popularly known as 3D printing. Now, it is the old classification of additive manufacturing. It's a liquid-based additive manufacturing process, solid-based additive manufacturing process, powder-based additive manufacturing process. This classification is based on the initial state of raw materials. And the liquid-based additive manufacturing process, the first additive manufacturing process in the world is the SLA, stereo lithography apparatus. Other than that, there are many other like SGC, SCS, solid-based additive manufacturing. The oldest one is the LOM, laminated object manufacturing, and the FDM, fused deposition modeling. One of the promising additive manufacturing process is the powder-based additive manufacturing process, and the oldest one is the selective laser sintering. And next to the 3D printing that is developed by the MIT, and the 3D printing name coined by MIT Boston in their product, where they have used the powder and glue, the binder-based additive manufacturing process. But this classification is no more valid now. As per the ASTM, the additive manufacturing process are classified into 7 groups depending on what is the methodology used for adding material layers after layer. So first one is the photopolymerization, then sheet lamination, material extrusion, binder jetting, powder waste fusion, material jetting, and direct energy deposition. So these are 7 categories of additive manufacturing process. And I like to discuss about what are the methodology used in this particular 7 categories, and what are the materials used, and what are the advantage, disadvantage, and limitation, and what type of research is required in respect of the materials or material bonding. So that particular part we like to highlight here. Now, material for the additive manufacturing, the material, there are the initial state. Three ways the materials is used, 3 categories the material is used: liquid-based materials, solid-based material, and the powder-based material. Now, liquid-based, there are the different types of resin, different types of photopolymer is used in liquid-based additive manufacturing process. So liquid materials, and the liquid material is used in case of a SLA, SGC, SCS, and SOUP. There are the different solid material or solid base, like in a form of a wear, in the form of wear, or in the form of a sheet, it will be used. That is the solid based material. In it, where may be made of a polymer, where may be made of your metal. It may be stainless steel, maybe the titanium, or maybe any alloying material. it can also be in a sheet form, either in your paper or your polymer sheet or the ceramic sheet. So there are the different kinds of sheet is used. Sheet form is used in a loam process, laminate object manufacturing, and filament or wire-based wire is used in case of a fuse deposition modeling. Material is also used in a powder form. So that is the most promising one, powder-based material or powder-based additive manufacturing is much more promising than the others. So powder may be polymer powder, or it may be the different class of metal powder, or it may be the your ceramic powder. So the powder is used in SLA process, 3D printing 3DP process, which is coined by MIT. And another form in the liquid materials is the ink based. The nanomaterials or nanoparticles. It has been formed in ink form, like your silver nanoparticle ink has been used in your different inkjet printing system, so that your material can be used in a liquid based, or it may be solid, or maybe powder. So we like to discuss about all three categories and the material generally used in the the categories, not all. For example, in powder category, all polymer is used, metal powder is used, composite powder is used, and ceramic powder is used. So in case of your liquid based, there will be a polymer, there will be nanomaterials in form can be used. In case of your solid based, like filament based or the sheet based, there is use of a polymer, there is a use of metal, there is a use of composite, and there is also use of sometimes some special case is the ceramic. So these are the different categories of material is used in additive manufacturing process. Now I like to show you some application of additive manufacturing process. After that, the principle. So quickly I like to show you this one. So you can use for art part, any prototype development, architectural, the clothes development for furniture, lots of gear you can manufacture, fashion accessories, in biomedical prosthetic, in shoe industry, you can develop your own robot. So possibilities are unlimited. Hello, am I audible?
Yes, sir.
Yes, sir, we can hear you.
Are you getting the sound of the videos, or I like to demonstrate that one? I don't know whether, are you getting the sound?
Yes, sir.
We are getting sound also.
Okay. Sure. I like to show you a few examples.
Change in the world we live in. They allow us to imagine and create works of art in a new way which was never before possible. This new technology daily used tools. So let's take a look at the best 3D printed creations. At number 10, the walking gyroscope. Invented back in 1980.
So here most of the parts of this gyroscope is developed by 3D printing.
Houses a spinning gyroscope which is geared to a pair of walking feet. You can even build your own, since the 3D model can be found on thingiverse.com. So make sure you check my description and click on the link to this 3D toy. That's number 9, the CNC multi-tool machine. Although it's not quite a 3D printer, this CNC machine is mostly made from 3D printed parts and is a lot cheaper than your average machine. It can work with woods, plastics, and even some metals. So I think I'll make sure not to incorporate an AI program into my next 3D printer and create a robot revolution. And like the last object, it can be found on thingiverse.com. At number 8, the Cortex cast. This exoskeletal cast is designed to replace their usual plaster forms. It is fully ventilated, super light, shower friendly, and stylish. An injured patient would first undergo an x-ray and then a 3D scan, and then a fully custom 3D cast is printed out. So this is definitely innovative and very beneficial to people who have to deal with an injury. At number 7, the dodecahedron speaker. With 3D printing on your side, building a complex speaker box becomes fairly easy to do. This 12-speaker array gives off great sound while being exponentially cheaper than some of its commercial counterparts. I expect to see and hear pretty cool 3D printed speaker housings in the near future. At number 6, the Forms of Nature light sculpture. This unique light casts 360-degree shadows onto its surroundings, which gives the illusion of being in a forest. New custom 3D lights are being designed and developed all the time, including this Minecraft cube and this jellyfish lamp. So lighting possibilities are endless when it comes to 3D printing. At number 5, the 3D printed 22RE 4-cylinder engine. This does not run on fuel like the real engine. It's actually a replica composed of many 3D printed parts. Built by Eric Harrell, once again, you can visit Thingiverse.com and print your own replica engine, but it'll likely take you over 70 hours to print. Every part moves, and it's driven off an electric motor. And if this is not crazy enough, the same creator even built replicas of a 5-speed transmission and a transfer case. So that's pretty crazy. At number 4, the Locomotor's 3D printed car. Most of this car is composed of ABS plastic reinforced with carbon fiber. Its frame, exterior body, and interior features only take about 40 hours to be 3D printed. Its mechanical components, which consist of battery, suspension, and brakes, are not 3D printed but are added on after. It's a fully electric car with a top speed of 50 miles per hour, and it's expected to be released next year. At number 3, a real 3D printed jet engine.
The metal 3D printing.
Engineers at Monash University. This new engine proves that 3D printing methods can cut costs and production times. Its creators are hoping to test fly a prototype within 10 months. If everything goes well, commercial certification will be awarded in the next 2 years. 3D metal printing is a fairly new thing and will not only improve engine building times for the aviation industry, but also for the automotive and marine sector as well. At number 2, the Porterhouse scaled model. This project tested the boundaries of large-scale 3D printing and brought forth a very unique nest interlock style type of house. Okay, it might not be a house which everyone would want to live in, but it does show that 3D printing can help us design and invent futuristic environments. Another really cool project is the Jane High Lake Resort in Beijing. It reveals 3D fiber reinforced cement walls and even several prototype agros have been built. At number 1, the 6-story printed apartment building. Built in China by Wingsun. It's a 3D.
So such type of building can also be developed in India in the last few months by additive manufacturing or 3D printing process. Now I like to talk about the most oldest one of the old additive manufacturing process, laminated object manufacturing. Quickly, I like to tell you. So this is material used in the solid sheet coated with a heat activated glue or the thermoplastic adhesive. It may be paper, plastic, composite, or ceramic in a sheet form, and thickness is 0.05 to 0.25 millimeters. And the process is the laser cutting and lamination by the hot roller compression. And the laser used is CO2, and this is the laser power. If you see here, this is the this is the build platform. And this is the roll, and this is the build platform. Over the build platform, you put the roll and takeoff roll. This is the laser, and there is the XY control of the laser. According to the cross-sectional information of the object, that laser will traces the path. Laser will traces the cross-sectional outer boundary, inner boundary, and there is an outermost rectangular boundary, so that this rectangular boundary is required whenever the platform is lowered down. The whole rectangular portion will lower down with this platform, and you just see unwanted portion. Only the annular circular portion is the cross section, and other is a cross hatch. Why cross hatch? That I'll tell you, it can easily remove the unwanted portion. Now, once one layer is over, the platform is lowered down equal to 1 layer thickness, and that time takeoff roll will start on, and a fresh paper will come over the previous paper. Now, what are the things that this hot roller will move over that, and hot roller will apply the temperature, heat, and the pressure. And below this paper backside there is a glue, that is thermoplastic adhesive. Because of the pressure and temperature, it will activate and it will adhere with the previous layer. So now second layer cross-sectional information, laser will traces the path the same way. The second layer is over, then again platform is lowered down, then takeoff roll will switch on, the fresh paper will come over the second layer, and the roller will move, then a third layer paper will adhere with the second layer, and this process will continue till the topmost layer will come. So this is the process is used in laminated object manufacturing. Quickly I like to show you. So this is the process. This is the tracing of XY movement of the laser, hot lamination, So it's a laser cutting. Then the fresh paper and the pressing. They basically lamination process. Now, ultimately, what you will get like this kind of things, and because of the cross set, small tile you can easily remove. For example, you see, you will get this box, you can remove. You can remove this way, unwanted portion, you will get your portion. But here the material wastage is more, so that is why this process is nowadays obsolete. And this is the machine which is basically procured in same area Durgapur long back in the year 1998. This is the loam process. So the modern machine, you just see modern machine is like this. See here the XY movement, plastic sheet has been used. See, once it is over, layer by layer addition, so you will get this one, remove the unwanted portion, ultimately you will get your object. Now I like to tell you the first additive manufacturing method in the world by photopolymerization process. The process is stereolithography apparatus SLA, and that is developed by the Professor Hall in the year 1988. He commercialized this one in 1988. He is the founder of 3D system, and this is the first additive manufacturing machine or first 3D printer in the world. And what the process is, it is the liquid-based additive manufacturing process. Photocurable resin is used, either epoxy resin or acrylate resin, and laser is used for the curing. Now here the process, you just see the process is simple. In this particular, this is the build platform. Initially the build platform is here. So I like to show you here the build platform is initially at this point, and over that one layer of liquid resin. Now according to the bottommost cross-sectional information, laser will traces the path. In this case, laser will not only traces the path like this and this, it will also traces inside, so that due to the interaction of the laser and the liquid resin, the photopolymerization process start, and because of the photopolymerization process, it will cure the whole cross section. This particular desired cross section polymer will cure the other portion, like here as well as here, it will be uncured polymer over the build platform. Once one layer is over, the platform is lowered down, and because of the lowered down equal to the one layer thickness, and the liquid resin from the surrounding, it will cover the previously cured layer. And in order to uniformly distribution of the over the previously cured layer, one vapor blade is used. And once the second layer is ready, then again a laser will trace the path, cross-sectional trace the cross-section according to the second layer cross-sectional information, and laser power has been controlled in such a way it will not only cure the second layer but also create the bonding between the second layer and the first layer, and this process will continue till topmost layer will come. And this is the machine, and this I can show you a little bit of this. See, this is the laser tracing has been taken place. You just see laser tracing, then platform is lowered down, then the vapor blade move, then again second layer is tracing, and this process will continue till the topmost layer will come. And ultimately, once it is top over, then the platform will move upward direction, and the partially cured solid object will get. Now you have to do some post-curing operation to make it fully cured, and these are the product developed by the SLA process. So these are the micro SLA, the micro parts, like biomedical parts or the precision gear, and we manufactured by the micro SLA process. I like to show you, these are the example of the micro SLA. So it is mostly used in the dental application. So next to the very common additive manufacturing process is the material extrusion based method, the FDM, fuse deposition modeling. Most of the colleges and academic institute have this one because it's relatively less cost, and it's relatively less running cost or recurring cost. What are the method? It is solid based additive manufacturing method. Here the material uses the different kinds of polymer, ABS or PLA or any kind of elastomer. So that first machine is developed by the Stratasys, and basic process I like to tell you here. This is the basically nozzle, the building nozzle, and the material, input material, in the form of a filament or the wire. So our diameter is 1.25 millimeter diameter, and that fed into the temperature control and X-ray position control the extrusion chamber. The process is very simple. Because of the feeding roller, the filament is continuously fed into this particular nozzle, and because of the temperature, it will become semi-solid, and because of the back pressure, it will come out from the nozzle of 0.4 millimeter diameter. So thin layer will be deposited, and the nozzle has to be moved in XY movement to deposit the material according to the cross-sectional information. Once one layer is over, deposition is over, the deposited platform is lowered down equal to one layer thickness, then second layer will deposit according to the second layer cross-sectional information. And this process is sometimes we are jokingly called, this is some like a jalebi making process. In the jalebi making process also we are doing the same thing. So there is a nozzle, cloth is basically a nozzle, there is a hole, nozzle, and by hand we are giving the back pressure, and by hand we are controlling the XY movement, desired shape of the jalebi. So it's like that, that simple process. I like to show you through the videos.
This production grade strength to weight ratio of its parts. The data is then
So this is the filament roll.
layer by layer on a build platform.
One is the build material, another is the support material. Support material you have to remove.
Like spools of thermoplastic and support material are used to create each cross section of the part. Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material upon the preceding layers.
So white one is the support material. See, this is the overhang structure, black one. So white material support is required.
The extrusion nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer. The finished part is removed from the build platform and cleaned of its support material.
Remove the support material for the overhang structure. So this kind of post-processing is required. So these are the different process parameters. This is the model developed. Next one is the powder-based fusion, one of the most promising additive manufacturing process, the selective laser sintering process. It is the powder-based. Different kind of powders is used: polycarbonate, nylon, wax, glass-filled nylon, powder-coated metal, ceramic is used, and process is sintering. It is very well-known process. So it will apply the focused heat to fuse the powder in the surface, and it will adhere with the nearby powder. And this process, you just see the steps. It's similar to SLA, selective laser. Instead of liquid resin, here the powder, and the powder will spread. One layer of powder will spread over the build platform, and laser will traces the path in such a way that it will not only sinter the material on that, it is sintered the layer, that particular layer, and then once one layer is over, then build platform is lowered down equal to one layer thickness. Then the again second layer of powder will spread. Again laser will traces the path according to the second layer processing information, and laser power is controlled in such a way it not only sintered the second layer, and it will create the bonding between the second layer and first layer, and this process will continue till topmost layer will come. So SLS and SLA difference: in SLA there is a liquid, and SLS there is the powder. So the other thing is remain same. Processes remain. Unsintered powder could be reused. So that is why here the wastage is very less. So I like to show you this thing in the video.
Cross sections or layers. The data is then transferred to the SLS additive manufacturing equipment. The machine then begins to create the first layer. After a leveling roller spreads a thin layer of powdered material across the powder bed, a CO2 laser traces the cross section of material.
So this is the tracing material. Deposition of powder, then scanning, laser scanning.
Once a single layer is complete, the powder bed is lowered to make room for the next layer. More material is introduced in a powder cartridge, and rolled out smooth, while unused material is recycled. The process is repeated, building layer upon layer until the part is complete.
So this is the process, layer after layer.
Less parts are built.
So you can use the metal powder as well. So you just see here.
Manufacturing technology that creates metal parts directly from materials.
So these are the parts you can manufacture by the SLS process.
Creates metal prototypes, high temperature application, manufacturing technologies.
See,
These sections will act
cross-sectional information fed into the machine.
exactly where to sinter MLS equipment.
See,
The laser then draws a 2D cross section on the surface of the build material, heating and fusing the material. Once a single layer is complete, the base plate is lowered just enough to make room for the next layer. More material is raised to the cartridge and recoated evenly on the previously sintered layer. The DMLS machine continues to sinter layer upon layer, building from the bottom up. As the part is built, support structures are added to give supplemental strength, fine features, and overhead.
so this way, by adding material layer after layer, you can develop any complex shape object, even metal object. So next is methodology, the binder jetting principle. So here the difference is with respect to SLS, instead of laser, here glue will be deposited through the tiny nozzle, and instead of laser, the glue will adhere the powders or metal powder or ceramic powder or any polymer powders. And this particular product has been developed by MIT in Boston. So this product, as you see, so this is the glue depositing head. Binder jetting principle, because instead of laser, binder will deposit according to the desired cross section. One of the important application of the binder jetting principle is in the foundry industry. You can develop the sand mold directly instead of making the pattern, so it will reduce the process cycle. So this is the one of the very important and very promising application of the binder jet principle additive manufacturing process to develop 3D printed sand mold. I like to show you this one little bit. You just see. So here, so this is the spraying of sand powder spraying. Then according to the cross-section information, glue has been spread over the sand powder bed. So in this way, you can develop the 3D printed mold, and you can carry out the casting operation. So patternless casting is possible nowadays. Next category is the material jetting. So instead of glue jetting directly, your liquid polymer will be jetted over the control UV environment, and as it is deposited in the control UV environment, it will cure. So that is polyjet. So here the material is deposited from the tiny nozzle. The material jetting process. So last one is the direct energy deposition. Here also metal powder is used along with the focused laser. So there is a concentric nozzle from surrounding. There will be you see in middle there is the focused laser, and from this two side there will be a powder, and there is interaction of the laser and powder, and it will melt and it will deposit over the platform. So this is the DMD, direct metal deposition. Another thing is nowadays is very popular, the metal wear based method. It's basically welding based additive manufacturing process. It's known as wear arc additive manufacturing process. It's similar to the welding process. Here the wear is used, metal wear is used, and welding principle, either TIG or MIG or laser beam, electron beam, plasma arc, any methodology used here, where the material will melt and it will deposit. So this is the wear arc additive manufacturing process for metal additive manufacturing. So I like to So this is the process you just see. The robotic welding process, welding method has been modified to the wear arc additive manufacturing process. So this is another promising additive manufacturing process where you can do metal part. Or it can also use for, say, a repair of the part. So this is the example of robotic additive manufacturing process. I like to skip, because I think there is a sort of, I like to skip the additive manufacturing for the level. So in inkjet printing system is used in the micro and nano additive manufacturing process for the flexible electronic device, PCB making, MEMS device development. These are the application of inkjet printing system. Now, inkjet printing system, the thermal inkjet and piezo inkjet, we have developed one thing. This is the example of your piezo inkjet principle, but there are some drawbacks in the conventional thermal inkjet and piezo inkjet that can be eliminated by the electro-hydrodynamic inkjet printing system. So we developed this setup in our DST project in collaboration with CMRI Durgapur and NIT Durgapur. So this particular process, electric field is used in between the nozzle and the substrate to pull the ink from the nozzle, and in order to create the nano droplet of the ink, and the ink used in the graphene inks. So I think in your lecture schedule there is a topics, the graphene by Professor Himadri Chattopadhyay. So there you know what are the wonderful materials, the graphene. Here graphene ink has been used to print flexible electronics display kind of thing, or the sensors we have developed. So these are the application areas: thin film display, flexible electronics, sensor, automotive, and aerospace area. Now, as I mentioned, these are the materials used in additive manufacturing. Metals are the plain carbon steel, in metal, like the plain carbon steel, your tool steel, stainless steel, aluminum alloy, nickel based alloy, titanium, copper. So this material is used either in wire form or in a powder form. So there are the newer and newer alloy material are now developing for the additive manufacturing process. Truly speaking, till date there is a material limitation in additive manufacturing. There are polymer is used, as you have seen the different process where the polymer is used. There are the use of sand, ceramic, there are the use of wax. So these are the material option, and obviously the additive manufacturing process is used nowadays in biomedical sector. So biocompatible material is also important in respect of additive manufacturing. If you see that there is a polymeric material, metal is used, ceramic is used, and also you just see some composite is used. So these are the different areas where the lot of research is required to make additive manufacturing process more effective. So these are the zones that I have shown: the ceramic polymer composite, ceramic metal composite, metal polymer composites. So polymer used are the thermoplastic polymers like ABS, your PLA, there are the different nylons. So these are the thermoplastic polymer is used in the FDM process. In the most of the college you can see there is the FDM printer which is use this, and along with that FDM you can use the different carbon fiber and different composite materials. So the composite 3D printed is available, that is based on the FDM process. So there are also thermoplastic polymer as well as the your fiber, the carbon fiber, both has been used to make a composite 3D printing. Thermosetting polymer is also nowadays people are thinking over that. Thermosetting polymer is used for the composite printing, which is mostly used in your say the space research and the defense. So both ISRO as well as the DRDO trying to develop a additive manufacturing system using the thermosetting polymers. And elastomer is another materials which is used in additive manufacturing process. So we like to show you, we have also used the elastomer, the polyurethane in our product development using the fused deposition modeling. So we have developed a 3D printed mask in NIT Durgapur, so that made of a elastomer. So previously we have developed the ABS based, but it is rigid. So we need some flexibility over the marks. It should be flexible enough, and it should be soft. And we have replaced by the ABS by the polyurethane elastomer, and it can take a shape of your face or like that. It will relatively the user friendly with respect to the skin and with respect to the the face movement during talking and others. So that is why this is another interesting application of the elastomer for 3D printed masks in this COVID situation. So these are the different materials used in the very popular additive manufacturing process FDM. It's like PLA, ABS. It has a lot of flexibility and easily available. It can easily extrude. But the only thing is the whenever flexibility is required, the PL and ABS is not good. That time you have to go for the elastomer like PU or polyurethane. So polyurethane, one of the relatively better material in when the flexibility is required. Now there are the metals. There are the different types of metals. Ferrous, non-ferrous metal is used in additive manufacturing. So the non-ferrous material like your aluminum, nickel, copper, magnesium, and its alloy. And ferrous material, the stainless steel and different types of alloy steel is used either in powder form or in a wire form in either SLS or the DMLS or in a wire car additive manufacturing process. So metal obviously have a good strength, toughness, machinability, but till date getting the surface finish and is very poor in a metal additive manufacturing process, and also you will not get the strength which you will get by the metal forming process. So in powder based method, you can use the polymer powder like thermoplastic or the polymer composite or nylon or elastomer. In metal powder you can use, and in ceramic also used in a powder form in biomedical application and in other structural applications. So ceramic is used. And as I mentioned, one of the important areas in additive manufacturing, one important application in additive manufacturing, the biomedical sector, implant development or the different types of dental application and ortho application. So that the different bio-friendly material is used. So biomaterials are used either in powder form, okay, and it can be added by either laser or by means of a adhesive or glue, or it can also use in a wire form. So titanium-based biomaterial, magnesium-based biomaterial, there are two promising one, along with the stainless steel and the bioceramic. So another important area is the bioceramic-based material for implant development, for the scaffold development. So a lot of research is required in this particular area because it is the one of the important areas in additive manufacturing, because you know that here the mass production is not required, mass customization is required, because the implant geometry is different from one patient to another patient. So you cannot develop, suppose a knee replacement, knee geometry is different from one patient to another patient. You cannot mass produce that part.
Hello. Hello. Sir, next speaker is waiting. So could you please complete?
I just conclude. I like to conclude. Okay.
Okay.
Sure. So another important area is the functionally graded materials. So different layer having different properties. That can be possible by additive manufacturing process. So these are the unique capabilities of additive manufacturing process. Any complex geometry you can build, and any complex material structure like functional graded material material component you can develop by additive manufacturing process. So this is at a glance. This is the different additive manufacturing process and its material and its strength and weakness. And I like to share here, these are the present status. You see that there are the different areas in the biomedical. This is the percentage share of additive manufacturing process in aerospace, automobile, even biomedical is 11%. And the future is it's exponentially increasing its application, its flexibility. Its advantage you already know. I already explained. Any complex geometry can do. There are less wastage of material and different without tooling or mold, you can develop any complex separate object. But there are the challenges in additive manufacturing. Material option still limited. Strength is not which you will get by a conventional manufacturing process. Accuracy and finish is also not good till date. So a lot of research is required in this particular area So the similar type of challenges in micro and nano additive manufacturing process, and these are the future research area. You have to synthesize the relatively newer material for additive manufacturing process, because materials in the macro scale and material in nano scale, the property is completely different. You have to take advantage of the materials in additive manufacturing process. So we have to synthesize new materials to get better strength, better surface finish of the product by additive manufacturing process. Along with that, process modeling and optimization is another important, because material and material processing is very important. So process modeling and process optimization is so the future research, in order to develop our indigenous additive manufacturing process, material research is much more important than the mechanical and electronics portion. So as far as my knowledge is concerned, that material modeling, material development is very much important in respect of the development of indigenous development of additive manufacturing process. Okay, thank you for your kind patience.
Thank you, sir, for your lecture. Now we will move to our next speaker. Our next speaker is Dr. Pramod Kumar. He's from University of Free State, Bloemfontein, that is South Africa.
Tanushree.
Yes, sir.
Next speaker is Professor Natarajan. See your mail. Professor Natarajan. Hello.
Okay, sir.
I'm here. Yeah.
Okay, so already the introduction have been given.
Yeah.
So before, so I'll request Natarajan sir to please take over the session.
Thank you.
You share your screen.
No,
Natarajan sir.
yeah, I'm uploading the file. Check.
Okay. Okay, fine. It is visible. Okay.
Okay, it will be okay this time. Okay, I'm able to see all of them. So shall I start the session?
Yes, sir. You can start now. Yes,
I can share them. I can give the video.
Yes.
Yeah. So good morning to everybody, and I thank for the opportunity given me to present my lecture. I'm sorry that in my last session there were some technical glitches, hence I could not complete my lecture. Anyway, the first part was completed. To recap, I am just going through the first part again, a little bit of it, not much of it. So the computer-aided drug design of flotation collectors, we finished in the first part, and I will be concentrating more on the second part, that is application of mathematical chirality descriptors in drug discovery. On the overview was presented there. So last session, I presented that molecular similarity clustering that is extensively used in drug design. We try to extend it for the synthesis of flotation collectors because flotation collectors are very important in the mineral processing. If the collector can concentrate mineral to a very small amount, then that will reduce the chemical consumption the further downstage. And therefore, we were very much interested in synthesizing new collectors, as there was no scientific method to develop new collectors. Actually, many of them were tried by trial and error. So we want to develop. That is how we have chosen a well-proven method, namely similarity-based clustering, and that has been extensively used in medicinal research. And we used that, and I explained part of it, where we converted molecular structure into molecular descriptors, and using the descriptors, we cluster them. And once we cluster, we can separate from each cluster. That means similar molecules are clustered together, like birds of the same feather, they flock together. Same way, the compounds which are very close in the molecular structure, they will come to different clusters. Now, what we can do is, if we want to synthesize 10 compounds, make 10 clusters. From each cluster, you can take one compound and then check. Or if you want to make even 20 compounds, you can select one from the farther, one from the middle, so that we can select 20 compounds and do the synthesis. And this is what I have shown here is a very hypothetical structure space, similarity space. But in the real field, when you do the analysis, the cluster of the structures will be only like this. And from each cluster, we'll be selecting one compound, and that will be synthesized and used. That is the outlay of the method. We try to synthesize new type of collectors for the flotation of sphalerite zinc mineral, because zinc minerals, they need at least 1 kilogram of copper sulfate per ton of the ore to get concentrated. Copper sulfate is a very expensive and corrosive chemical. We want to eliminate or at least reduce its consumption in the flotation process. So we tried a new series of collectors, and instead of just going by trial and error, we developed a database or a structural base of 1,000 compounds. From the 1,000 compounds, by molecular similarity, we selected 20 compounds, and of the 20 compounds, one was called this is the best performing collector, and it could float zinc mineral, that is sphalerite, by using only reduced amount, that is half of the amount of copper sulfate. However, it floated iron mineral, that is pyrite, along with sphalerite. When sphalerite is concentrate is contaminated with pyrite, the value of the concentrate goes down, and it goes down by a rate of, that is, per 1 ton of the ore, it goes down by $1. Therefore, pyrite coming up in the concentrate is a detrimental factor. That means, though we found a scientific method for synthesis of collectors, the collector we synthesized is not very selective for zinc. Therefore, we wanted to go and try the next series of collectors. And for the next series of collectors, what should be the base or the skeletal structure? We searched from Mother Nature. That is, whatever is done in the by Mother Nature, she does it very effectively and efficiently, because nature, it is a millions of year evolutionary process. Lot of trial and errors have gone. So whatever Mother Nature does, she does very well. Therefore, we search for zinc in many of the biological molecules. There is a class of protein called zinc finger protein. The zinc finger protein, zinc is always bound to nitrogen atom and sulfur atom in the amino acids. Therefore, we thought that the new collector that we are going to synthesize should have a nitrogen and a sulfur at least. And they should be able to form a chelate, that means a ring structure with the metal atom in the mineral side. But this compound is called aminothiol. So we created a database of about 200 compounds, and we did a similarity clustering, and we selected these compounds and tested, and we were able to find that the collector was very aminothiol that we synthesized are very effective, and they are very selective for zinc mineral. They floated pyrite, but very, very small amount, small percentage. That means the pyrite contamination is less than what is being achieved in even present mill operations. And the copper sulfate consumption is very much reduced, unless otherwise zinc mineral is suppressed for the flotation of some other mineral. we need activation. Otherwise, even activation by copper sulfate is not necessary. However, in the current mill process, comparing that, we need just 200 gram per ton. Where see, the present mill processes, they use 1 kilogram of copper sulfate per ton. But now we have reduced it to 200 gram per ton of the ore. That means we reduce the copper sulfate consumption. In an industry or mineral processing unit that processes about 200 to 300 tons of ore per day, they'll be using about 200 to 300 kilograms of copper sulfate. That is reduced by 25%. Therefore, the new collector is very selective. We are able to float zinc effectively, and copper sulfate consumption is reduced. And this new collector is patented, and we have received both the Canadian and the US patent for this mineral. And this is the best performed, that is, we call it N-butyl aminothiol. So this compound is the best collector. So this research explains or outlines how a well-proven process used in a different field, namely medicinal chemistry or drug design, we have borrowed that idea and used it effectively in a chemical engineering field, where we synthesized new type of chelating molecules, collectors, and we are able to get a collector that is very efficient for the flotation of colorite. And this research was carried out in the chemical engineering department of Niketan University under my group leader was Dr. Natarajan, who was Professor. So this is just a recap of what I presented in the last lecture. Now, this part of it I couldn't present the last time, therefore I am trying to represent it now. So this research was carried out under the leadership of Dr. Subhash Basant. I think you must have, many of the audience would have heard Dr. Basant. On the opening day, he had a session. And this research was carried out in the Natural Resources Institute, the University of Minnesota Duluth campus in US. This lecture is a little bit fundamental chemistry oriented, but it will be interesting, and we'll be posing some new areas or domains where engineers can also contribute with the knowledge of fundamental chemistry. I'm going to the phenomenon called optical activity. What is an optical active compound should have at least one asymmetric carbon atom. What is an asymmetric carbon atom? An asymmetric carbon atom is one that is attached to 4 different substituents. That means that 4 different substituents are entirely different. That means they don't relate to one another. Otherwise, we can say this molecule does not have a point or plane of symmetry. In mathematical terms, it doesn't have a plane or point of symmetry. If A is equal to A on this set, D is replaced by A, then it will have a plane of it will have a plane of symmetry. That's why it should not have a plane of symmetry. The absence of symmetry, we call it asymmetric carbon atom. Therefore, if this process, or if you place these 4 substituents in space, they can generate 2 structures. The 2 structures which are different in spatial orientation are related as an object and a mirror image, and they are related otherwise as the left hand and right hand, whereas the left hand is a mirror image of right hand. Same way, this compound is a mirror image of this compound. Therefore, this mirror image relation is called, or the handedness is called chirality. These 2 forms, they interact differently with the plane polarized light. If one rotates to the right hand side, the other will rotate the plane of polarized light towards the left hand side. The one which rotates to the right hand side is called a plus isomer. The one rotates towards the left is called a minus isomer. Otherwise, using these terms, this is called dextrorotatory and this is called a levorotatory. And these 2 are related as optical isomers. And because I said, because these 2 are related as object and the mirror image, not just the mirror image that cannot be superimposed. If you cannot place one over the other, that means the 2 isomers are related as object and mirror image that are non-superimposable. So Lord Kelvin, the one who introduced the term chirality meaning handedness in Greek. Therefore, the word chirality was introduced by Lord Kelvin. Now I am taking a simple example. Many of you would have gone through this even in your grade 12 classes. So lactic acid, this is a carbon. This is asymmetric carbon, or we call it a chiral center because we introduced the term chiral. This is this is hydrogen. This is that's a mistake. This is hydroxy OH. Therefore, these 4 groups are entirely different. When these 4 groups are different, this And these two are related as the object and the mirror image. This is rotating the plane of polarized towards the right. That is called a plus isomer or nectorotatory. That means its mirror image will rotate it towards the left-hand side. That is called the levorotatory. As I said, the two isomers are, from this point of view, we try to use the word enantiomers. So enantiomers are therefore the object and the mirror image isomers, which are non-superimposable. And because they differ only in the orientation in space, that means anything in 3 dimensions, we call them as a stereomerism or stereo speakers, so they are called stereoisomers. Now, to differentiate stereoisomers in chemistry, they use different notations. And sometimes these notations are very confusing. Let me make it clear to the audience. We use the term plus and minus to denote the two isomers. And I explained in my previous slide, plus isomer rotates to the right-hand side as it is positive direction. Minus isomer rotates the plane of polarized light towards the left-hand side, at the negative side, which is called plus and minus. The plus and minus may also be replaced by the word D and L. D stands for dextro, L stands for levo. Therefore, the D and the L are plus and minus. They denote the same. That is, that depends upon the intrinsic property, namely the optical activity. But that lowercase d and L are equals with uppercase D and L, DL notation. This is confined only to carbohydrates, or they call them as sugars and amino acids. In sugars, normally they have a CH2O group, and at the end they may have an aldehydic or a ketonic group. Therefore, the number of carbon atoms are 5 in the sugar, we call it a pentose. The number of carbon atoms are 6, we call it a hexose. For example, glucose is a hexose, therefore the CH2OH will be 3 times 1, 2, 3 CH2OH 2, therefore there will be 26 carbon atoms. But from the bottom we have to take that the second carbon atom, if the OH group is on the right hand side in the molecule, then it is called the D isomer. If the OH group is on the left hand side, then it is called the L isomer. Therefore, this is only with respect to, this is nothing to do, this uppercase D and L, nothing to do with optical rotation. They have to do only with configuration on the second carbon atom from the bottom of the molecule. The same is extended to amino acids, because amino acids are, especially we call them as alpha amino acids, because this acid group is next to the amino group is next to the acid group. That's why this is called alpha carbon. Therefore, we call them as alpha amino acids. Alpha amino acids are the building blocks of proteins. Therefore, the alpha amino acids also use the same notation D and L. Here, the OH group is replaced by NH. Therefore, when it is NH2 group is on the right hand side of, then we call it D, and it is on the left hand side, we call it L. And other than this, so the uppercase D and L, nothing to do with, they do not denote the optical activity. They denote only the configuration about the second carbon atom. And the another notation is RS notation. RS notation is R stands for right and S stands for left. That is sinister. So RS notation is used to do the configuration, not on the second carbon atom, first carbon, on every carbon atom. Therefore, at first carbon, what is the notation? What configuration? But second carbon, what is the configuration? That's how it is denoted. It will be denoted. The next slide, I explain you how to get the RS configuration. But when it is R, that means it may be R configuration for a particular, and it may be having dectorotatory or levorotatory. Similarly, with S configuration, it may have a dectorotatory or levorotatory. Again, I want to emphasize that R and S have nothing to do with optical activity. They are just configuration or how the various groups are arranged in space. That is for our understanding. Now, how we going to assign the RS configuration? That means, let us imagine a compound, because this is asymmetric carbon, this is methyl, fluorine, chlorine, bromine. 4 different atoms are there, or 4 groups are different, and definitely this is asymmetric. Now we have assigned priority based upon the atomic number. The group whichever is bigger will be given the highest priority. That means here bromine, which has a high molecular weight, atomic weight, is given priority number 1. That is, it is A. Fluorine is next, it is B. Fluorine is C. And if we don't go through the methyl, the first atom attached to this center is carbon. Carbon is atomic number 6. Therefore, it gets the lowest priority. Therefore, A, B, C, D is a priority. And if we take this example here, methyl hydroxy group, amino group, and hydrogen are there. Between oxygen and nitrogen, oxygen has atomic number 8, nitrogen has 7, therefore oxygen has a priority, nitrogen has next priority, then comes carbon and hydrogen. And to assign the configuration RRS, what we do is the least priority group is kept away from the eye of the from our vision. That means the D is kept away, and we look at this. Then if A, B, C are in the positive direction, that is in the right hand clockwise direction, we call it R. They are in the left hand side, that is anti-clockwise direction, we call it S. Otherwise, the three groups are arranged like these are the four groups, like the steering wheel of a car. So the three groups of higher priority are on the wheel, like steering wheel, and the fourth group is the stem of the steering wheel, that will be the axle. So that's for the least priority group. But here, if we arrange like this, in representing the chemical structure, we use a wedge formula like this. Broken wedge will not indicate that it is away from the viewer. That means for this molecule, when bromine, chlorine, fluorine are arranged like this, it is called R isomer. If they are in the reverse order, then ABC like this, then it is a S isomer. Then, why we introduce all these things? Then chirality is very, very important. It is very common among the natural systems. Always chirality, we call it handedness. The handedness is very common and prevailing among the natural biological systems. For example, all the alpha amino acids, the building blocks of proteins are all L in configuration, or they are L series. All the natural sugars are D series. That's why we call it D-glucose. D-glucose doesn't stand for dextrorotatory. D-glucose stands for it has a D configuration. Therefore, the macromolecules proteins, which are formed from the chiral building blocks of amino acids, also have chiral centers, and then number of chiral centers present in the proteins. Enzymes are also proteins, and the prevalence of the preference for the same type of handedness of chirality, we call it as a homochirality in natural systems. For example, proteins, enzymes are also proteins. These macromolecules are, as I said in the previous slide, they are formed from amino acids, and all the protein they bend, fold, and coil, and all these coilings are all right-handed. The protein is not having a left-handed coil; it always have a right-handed coiling. Then the drug molecule interact. Therefore, all these this is the protein molecule. How we represent the structure in the three-dimensional. Therefore, when a drug is going to interact, then there are a lot of these chiral centers, and this will go on. The drug molecule will go on bind to these chiral centers. Therefore, and I continue the same thing with the amino acids also. Sorry, nucleic acid. In nucleic acid, in DNA molecule is made up of sugars, phosphate sugars, and the four bases. And DNA is again a right-handed alpha helix. Therefore, it's again having a preference. It's not having a left-handed rotation. It's having a right-handed coil. Therefore, natural systems always prefer to have either left-handed or right-handed. We cannot see both the type of chirality business in natural systems. That means chirality is a biosignature of organic evolution, I can say. That is why any space mission is going checking to test whether to explore whether the possibility of life or evolution of life is going to take place. Always those space missions carry a chiral probe that will first search for whether chiral molecules with asymmetric carbon molecules are present in the atmosphere. If that is there, that means definitely the process of evolution is going to take place. That's why I'm repeating, chirality or handedness is a biosignature of organic evolution. How it is important for us in synthesis? Because, as I said, biological systems, natural biological systems are chiral in nature. Therefore, the receptors they act as the receptors when we take the drugs, some of the molecules when we take them in. And for example, the water perception is excellently differentiating the plus and minus isomer. I am not repeating every one of them. Even if you take lemonade, if it is a plus lemonade, it is orange in taste. If it is minus lemonade, that is a lemonade taste. Therefore, the water perception or the taste perception, they are very, very specific with respect to the molecule, the stereospecific or stereochemical structure of the molecules. Therefore, physical and chemical properties of the enantiomers are the same. However, they will be differentiated by biological molecules. So the plus isomer will behave in one way, and the minus isomer will behave in a different way when it reacts with it. But in laboratory synthesis or in industry, when you do normal organic synthesis, whenever you do a chiral molecule, we don't get, like in nature, we don't get a plus form or a minus form. We get always a plus and minus mixture. We call it a racemate or a DL mixture because D and L are present in 50-50%. Therefore, we call it a racemate or a DL mixture, that is inactive mixture. But that means the several drugs which are all chiral molecules that are synthesized and sold in the market are sold mostly as racemates. What is the problem when we are selling racemates? I will explain you this example of a thalidomide. We call it as a thalidomide tragedy itself. And this very clearly, this instant, this tragedy very clearly explains how a pharmacological or a biological system very clearly distinguished between the chiral molecules. So thalidomide was administered as a sedative by a West German company in 1950-52, I think. So more than 10, it was given as a sedative because it is called morning sickness for pregnant women, which is creating nausea. So to suppress the nausea, they were administering thalidomide as a medicine, and all those pregnant women who took thalidomide as a molecule or as a compound to against morning sickness, all the babies, more than 10,000 to 20,000 infants that were found in Europe alone from between 1952 to 1960, most of them have malformation of limbs. This was called Pocomelia. And this, initially, they couldn't identify this. You can see the malformation of limbs. You can see this side is not having the hands here. This is not having the hand. This doesn't have the proper leg. So for the kids should be formed with all sorts of limb abnormalities. So it is called the thalidomide nightmare. And why it has happened was not revealed, was not understood for many years, but later it was identified. Thalidomide was sold as a R and S mixture. As I said, it is a racemate. It was sold with a mixture of both the compounds, both isomers. Only the R isomer is having the correct medicinal property. That doesn't mean S isomer is non-active. On the other hand, instead of attacking that particular protein, S isomer went and attacked. This was considered only as an inactive isomer. R isomer, we call it as an active isomer. Whereas the S isomer is an inactive isomer. But inactive means inactive for suppressing nausea, but it is active in some other site. It went and attacked a protein called cerebellum, and that is how it has stopped the growth of limbs and all the messages that has to be gone for the formation of limbs. It was all inhibited. That is why these kids were born. Therefore, this thalidomide nightmare very clearly explains that it opened the eyes for the entire drug industry that don't imagine that if one isomer is active, that doesn't mean the other isomer is inactive. That is why often only one isomer is therapeutically active. That doesn't mean that the other isomer is inactive. It may be active for a non-target site, and that can lead to other abnormalities. And after this, the Food and Drug Administration came up with a new rule that whenever a company is selling the mixture of R and S isomer, or plus and minus isomer, which we call it as a racemate, even if one isomer is identified as active, they should test both for activity and what the inactive isomer, otherwise the other isomer will do. The toxicity profiling must be completely evaluated before selling those drugs. Therefore, racemates can be told, but pharmacological and toxicological effects of both isomers, enantiomers, as I mentioned, enantiomers are R and S isomers, which are related as the object and the mirror image. The enantiomers must be characterized. Now, after this, industries are going for synthesizing pure chiral molecules. And 80% of the molecules that are coming up in the industry in the last 5 years are all chiral molecules. 75% of them are now switched to our pure enantium. That means single isomer is present, the other isomer is not present, and 200 chiral molecules could enter at least every year. Then, I like to introduce you two terms that are extensively being nowadays used in the industry. One is called chiral switching, another is the repurposing. So, FDA has said that racemates cannot be used, can be sold only when you are coming up with the toxicological profiling of both the S isomer and the R isomer. But now, several companies which have a patent for the marketing the racemate, the plus or minus isomer, now they are coming up with only the active isomer, a single isomer, a single enantiomer drug, and in that case, they are able to re-register the patent, and the patent is extended. That is why they are switching over from a racemate to a chiral enantiomer pure drug that is called chiral switch. And with the COVID and the other situations, now several molecules or several drugs that have been used for a particular disease earlier are now being used for other diseases. This is called repurposing. For example, if you take some of the drugs that is tested for COVID-19, so I'm not going to go through every one of them. So Lipnover, then you got Ritonova, all these compounds, these centers are they are all chiral molecules. They are all chiral molecules. And chloroquine and hydrochloroquine, these two are the drugs used for malaria prevention. They are known for malaria, anti-malarials. But now, with COVID-19 situation, they try to use this. Therefore, a drug which is used for malaria is now being tried for COVID-19. This is what's called repurposed. So, chloroquine and hydroxychloroquine is repurposed. And you may be remembering that India is a country which exported more than 10 million doses of hydroxychloroquine, which is abbreviated as HCQ for hydroxychloroquine. You know that we were exporting to several countries. Then why are these things I'm giving you is on molecular chirality? When we go for chiral liquid molecules, we have to predict the property or the toxicological or pharmacological property of these chiral molecules. And to predict them, we have to convert them into numbers. That means molecular structure, not just the two-dimensional molecular structure, the three-dimensional stereochemical structure has to be converted into the number. And this mathematical characterization of chirality is very, very important because the drug industry is going through a transformation to synthesize more and more chiral drugs. About structure activity relationship descriptors are very essential. Now, in calculating the chirality indices that we have proposed in our laboratory, we assign, like I explained to you how to assign R and S configuration. Same way, we identify the 3-4 structures. The one which has got the substitute the highest priority is A. The structure, the substitute has got the next priority B, C. So the 4 groups that are attached to the chiral center, they are given marked as A, B, C, D in the priority. A has the highest priority, D has the lowest priority. Now what we do is, for each of those atoms or each of those substituents, we assign a weight. How do we calculate the weight? We can calculate the weight based upon the atomic weight of the substituents, add them all together, or we can have another algorithm like, but we can have the number of electrons in the outermost shell minus subtract the number of hydrogen atoms attached to that. So that is the way we can calculate the weight. Or we can have a physical chemical property of that particular part of the structure. So we can have any algorithm to assign weight. Once we assign the weight, we can calculate that. But if the substituent is having not just one atom, 2, 3, 4 atoms, then as it is moving away from the chiral center, we have a diminishing contribution to the chiral index. First atom attached directly to the center, we have 100% contribution. The atom is away by 1 carbon or 1 atom, then it is 50%. The third, if it is 3 atoms away from the chiral center, then it will have only 25%. It goes on. I can explain you this with an example. So this compound, so this is CH3OH, CH2, CH3. Therefore, this is a carbon which is attached to 4 different groups, chiral groups. Therefore, this is a chiral carbon. This is substituent 1, the group 1. This is substituent 2, substituent 3, substituent 4. Now we have to assign priority. We have oxygen, That means among all these, oxygen has the highest atomic weight, therefore oxygen has got the priority. Then between these two, this is carbon, but this is carbon, two carbon atoms are there, therefore this gets the next priority, and this gets a third priority, and hydrogen you know that as the least priority. Therefore A, B, C, D are the assignment. Now how we are going to assign the weights? So this is oxygen is delta. As for I'm giving you only one example of how we assign the weight. For oxygen, this group, over group, we assign the weight. Is by the letter delta. Delta is equal to number of electrons in the outermost shell minus number of hydrogen atoms. Oxygen number of electrons in the outermost shell is 6 minus 1 hydrogen atom. Therefore, the weight of this group is 5. Same way, the weight of this group we have to calculate. This is 4. Carbon has got 4 electrons in the outermost shell. 4 minus 2, that is 2. And this one is 4 minus 1, 3, therefore it is 1. But this carbon, it contributes 100% for the chirality index, but this carbon is 1 carbon away from the center, therefore it contributes only 50%. This is marked here. Therefore, the weight for this group is 2 plus 1 divided by 2, that means it is half, it is 2.5. For this group, T. So delta C, this one, let's start outermost electron in carbon is 4, 3 hydrogen atoms is 1. For hydrogen, the weight is 0 because hydrogen is not considered as a vertex when we are using the chirality. Now, how are you going to calculate the index? See, we call the chirality index as a relative chirality index RCI. Now, for the R isomer, as I told you, the fourth group, the least priority group is kept away from you. Therefore, this is the steering wheel. This is the 3 atoms, the 3 groups sitting on the steering wheel. So if they are on the right hand side, clockwise direction, we call it R. If they are on the anti-clockwise direction, we call it S. Therefore, to calculate the chirality index, we call it A, weight of A plus A multiplied by B. That is A plus AB, A plus AB plus ABC, then A, B, C. Therefore, this is the formula that we use. And for the S isomer, A plus AC, because the next I think is C here, we are coming when we come like this. So A plus AC, then next one is A plus AC plus ABC. So this is formula. So this was extended for the calculation of, see here it is 5. Say I am going back here, we assign the weights as for the previous molecule it is 5, 2.5 and 1. So we are calculating chirality index for this example. 5 plus 5 multiplied by 2.5. So you can substitute, all these values are substituted. For R isomer it is 52.5. For S isomer it is 31.5. That means the new chirality index that we have proposed is able to distinguish between the R isomer and the S isomer. It can be used for several other compounds. For example, on the other hand, somebody can ask the question, okay, you are talking about a molecule containing only one chiral carbon. But if the molecule is having 2 or more chiral carbon, what will you do? Calculate the chirality index or relative chirality index for each of those chiral centers. Then take the square of chiral center 1, square of chiral center 2, square of chiral center 3, and then divide them by the number of chiral centers. That means, and then take the square root. Make it short. This means we take the root mean square of the RCA value, right hand to chirality indices for the various chiral atoms molecule. Now we use this to calculate for the 17 amino acids. The amino acids they are given as R and S, and these blue, red, blue, and green they denote. As I said, when we calculate the chirality index, the weight can be assigned on various algorithms, and we have used 3 different algorithms, and all the 3 cases, R and S isomer, they have different values for every one of those molecules. And I have given only 2 structures which are highlighted here, cysteine and serine. Cysteine and serine are similar structure. Only thing is this is sulfur and this is oxygen. Sulfur and oxygen, they belong to the same group in the periodic table. Therefore, these types of groups are called isosteric. That means they have a similar bulkiness. Therefore, steric means bulkiness. Therefore, they have the similar stericness of isosteric structures, and isosteric, bi-isosteric molecules are having that. You can see that in one of them they have the same value. Okay. So the different chirality indices, one of them is able to identify the bioisosterism. Therefore, if the receptor molecule is looking for bioisosterism, we can use this type of chirality index. Okay. As I said, when we have more than one chiral center, what will we do? That is, for example, if you have two chiral centers, then with respect to center 1, you can have R, center 2 can be R and S, S and R and S, and therefore 4 stereoisomers are possible for a compound with 2 chiral centers. That means one can ask how many molecules, how many stereoisomers would be possible for a compound with 3 chiral centers. You can give it by a formula 2 power n, where n is the number of chiral. When it is 2, it is 2 power 2, it is 4. When it is 3, it is 2 power 3, then it will be 8 stereoisomers. Now we have taken 2 examples where we have got 4 stereoisomers. For R and R, RS, SR, SS, all the stereoisomers are having different values. That means the new chirality indices are the new mathematical descriptor we have given for distinguishing stereoisomers is able to work well and differentiate the various types of stereoisomers. Now, so the characteristics, what are the characteristics of the relative chirality index or the new descriptor that we have proposed? New chirality index are able to differentiate enantiomers, and even if it is having more than 2 chiral centers or 3 chiral centers, it is able to differentiate it. And we can assign delta value based upon any of the algorithms that somebody can imagine, based upon the weight of the substituent or based upon the size of the substituent, based upon the any physical property. So that is how we can calculate it. It's an open-ended formulation. So RCI, relative chirality index, can do distribution. That means it gives what does it encode finally? It encodes how the different groups are distributed or arranged around the chiral center in the model. Okay. Now the purpose of introducing is to predict biological properties. So we took, at the time we were working developing new mosquito repellents, and there was one repellent developed by US Department of Agriculture that we call it as USDA. The molecule was known as AA33720. Therefore, this is the structure of the molecule. So, this carbon is chiral, this carbon is chiral. Therefore, it has got 2 chiral centers. That means you have 4 isomers, stereoisomers. So, this can be R here, R and S. All the 4 compounds are synthesized. Chirally few compounds are synthesized and their proportion binding. That means when you apply it on your hand or on your body, we call it a topical repellent. For what is the percentage of mosquitoes that is biting somebody? When we use that means mosquito receptors are able to distinguish the 4 stereoisomers. That means the one which has got S and S configuration, only 18% of mosquitoes are biting. That means 82% it is inhibited. That means they are not biting. Yeah, it is 51%, 32%. That means the SS among the 4 stereoisomers, yes, the isomer which has got S and S configuration is the best mosquito repellent. That means even the receptor in mosquito, that is water and binding protein, is the protein that is responsible for sensing odors. That means mosquitoes attack us by sensing the carbon dioxide, ammonia, lactic acid, etc. emanated from our body. They serve as a cue and they come and attack us. So when this molecule goes and sits at the water and binding protein, it confuses a mosquito and drives away from us. That's why it is a repellent. And even the mosquito protein, the protein present in the mosquito proboscis is able to distinguish the stereoisomers and is able to bind it. And the gratifying are the information from this study is they are able to model the repellency. That means the biological or bioefficacy of molecules are able to be modeled. That means using the descriptor, we are able to form a regression model. That means proportion of binding by this 4 stereoisomer is given by linear equation, where the equation is chiral index is being used, and the R square is 0.96. The correlation coefficient is very good. Therefore, this gives the information, or the thing is the new chirality index, which is called the relative chirality index, can be used for the prediction of properties of stereoisomers. That means we can form quantitative stereostructure activity relationship models, and the relative chirality index can be used on different scales And once you can identify from the scale which chirality index scale is able to correlate very well with the property, that gives an indication of what type of handedness the receptor, the chiral receptor is looking for. For computer-assisted prediction of new drugs or the biological activity of chiral molecule is possible. Therefore, this type of formulation or numerical characterization of chirality will help very much in synthesis of new chiral drugs. So before I conclude, I'd like to say that this is a fundamental chemistry concept and it is being presented in a program of engineers. But this fundamental chemistry concept will lead to new areas where we can contribute. One of the possible areas where I'm looking at is because pharmaceutical industry is looking for synthesis of chirally pure compounds, but normal laboratory synthesis is always yielding both plus and minus. Therefore, we can come up with, chemical engineers can come up with new catalysts. A new catalyst we can allow the synthesis of only the one isomer or stereoisomer, maybe plus or the minus isomer. Therefore, catalysts for chiral synthesis or asymmetric synthesis, one area. The another one is, okay, we prepare, instead of preparing enzymatically pure compound, if our chemical method is yielding both the isomers together, we can have a separation. Therefore, we can come up with new systems or new phases. These new phases can differentiate and then separate the plus isomer and the minus isomer. Therefore, chiral separation materials can be identified by chemical engineers. And as I said in the beginning, chirality is a biosignature of organic evolution. So any mission, space mission that is taking place will always have a chiral probe. With the fiber optics technology and the nanomaterials coming up, we can come up with the new types of chiral probes. They are highly sensitive and can identify chiral molecules even in the concentration is parts per billion. For example, chiral nanomaterial can be fused into optic fiber and that can be used in the chiral probe. And all sorts of things are opening up because I'm repeating, the knowledge of fundamental science and can always lead to application, and that by engineers like you can apply it in an area. And I like to close my interest in that is India is a country which needs technology and young minds like you come up with new technologies that can be patented that only can make this country a superpower. I thank the organizers of this conference, the FTP program, and my special thanks Dr. Ashish Mitra and Dilip Kumar for making all these arrangements. And I thank Dr. Subhash Prasad who put me in contact with these people to arrange this. I thank everyone and thank you very much. Thanks for listening and any questions.
Anushree ma'am.
So thank you, sir. And I think in chat box we are not having any other questions. So we have shared your email ID with them. So if they have any query, they can just put the question to you through mail.
Okay.
Thank you so once again.
Thank you very much. Thank you, Dilip and Dr. Ashish. Thank you.
Thank you,
sir.
Thank you.
So our next session will start from 2 p.m. onwards. So it's for the participants that please join in time or before time, 10 to 15 minutes before. So for now, we are ending the session.
Prof sir.
হ্যাঁ এক্সিট করে দিই
হ্যাঁ ওকে এন্ড করে দাও হ্যাঁ